Okay, in the last lecture we have studied two properties of a sequence of functions, that is boundedness properties and term by term limiting properties. Now I am going to third properties, that is continuity. Continuity of a sequence of functions. Continuity of a sequence of functions means actually if fn d2 be a sequence of functions and fn are all continuous on the domain D, and also limit n tends to infinity fn equal to f, then whether f is continuous, that is the preservance of the continuity of the continuity property, whether it preserves or not actually. Now for I have taken an example, that is fn x equal to x to the power n minus 1 for x belongs to 0 to 1. We see that fn are all continuous functions on 0 to 1 because it is a polynomial function. Simply polynomial function always continuous, therefore fn are all continuous. But the limit function of fn is given by fx equal to 0 for x belongs to 0 to 1 open interval 0 to 1 and 1 for x equal to 1. Therefore f is obviously a discontinuous function at x equal to 1. So here you see that fn are all continuous, but the limit function is discontinuous. This happens because fn converges to f only pointwise, not uniformly. We already seen in the example, in the first example, that this sequence of function converges to f pointwise. Therefore, we see that the pointwise convergence is not a sufficient condition to be to preserve the property continuity actually. So in this theorem, in the next theorem, we see that if fn converges uniformly actually to f, then and fn are all continuous on D, then fn must be continuous. If we prove this theorem, then it will be established that the condition of uniformly continuity is a sufficient condition to be continuous of f. Just I am going to prove of this theorem. Let C belongs to D, C be any point of D actually, and epsilon greater than 0 be any real number. Since fn is uniformly continuous to f, therefore we use the definition of uniformly continuity. There exists positive integer k such that mod of fn x minus fx less than epsilon by 3 for all n greater equal to k and for all x belongs to D. This. Therefore we see that for this property satisfies for all n greater equal to k, therefore it also satisfies for n equal to k. This also satisfies for n equal to k. Hence we put n equal to k. Also this property satisfies for all x belongs to D, therefore it also satisfies for C, because we have taken C is an arbitrary point of D. Therefore we get two relations, mod of fkx minus fx less than epsilon by 3. This property holds for all x belongs to D, and in particular for x equal to C, mod of fkc minus f of c less than epsilon by 3. Again, given that fk, that is fn, are all continuous on D actually. On D means at any point of D. Therefore fk is continuous at C. Hence we can use the definition of continuity. Hence by the definition of continuity, there exists a delta greater than 0 such that mod of fkx minus fkc less than epsilon by 3 for all x belongs to nc delta intersection D. That is, for all x belongs to nc delta intersection D, actually we have to prove that f is continuous at C. That is, we have to show that for some delta, if we take x belongs to nc delta intersection D, then mod of fx minus f of c eta less than epsilon. Therefore we write this as mod of fx minus fkx plus fkx minus fkc plus fkc minus f of c. The terms minus fkx plus fkx minus fkc plus fkc removes out. Therefore by triangle inequality we get this lesser equal to mod of fx minus fkx plus mod of fkx minus fkc minus this, actually the last line. All the values of this, all the values of the terms less than epsilon by 3 we already got this. Therefore there are three terms. So mod of fx minus f of c less than epsilon whenever x belongs to nc delta intersection d. Therefore we obviously can say that f is continuous at x equal to c. Since c is any arbitrary point of d, therefore f is continuous on d. So we see that if fn are all continuous and fn converges uniformly to a function f, then f is also continuous. So we can say the condition of uniformly continuity is a sufficient condition to be continuous of fc. Naturally, a question arises that whether this condition is necessary. Actually, the answer is no. Because for this example, here we consider an example to show that the condition is not necessary. Not necessary means if fn is not continuous, fn, the convergence of fn is not uniform, then we may get f is continuous, where fn are all continuous. Here we take fn x equal to nx by 1 plus n square x square. In the last class we already seen that by mn test, actually fn convergence of fn is not uniform and it converges to a function f where fx equal to 0 for all x belongs to 0 to 1. Also fn are all, fn being actually rational function and the denominator not equal to 0 for all x belongs to 0 1 and for all n belongs to n greater equal to 1, actually. Therefore fn are all continuous and also f is continuous, the limit function f is continuous, but this convergence is not uniform. So uniformly continuity is not as a necessary condition for this result. In the next part we see that we give an application of the convergence application, actually, of this result to show that a convergence is not uniform. Actually, if we see a sequence of function fn converges to a function f, convergence means simply pointwise convergence first, what we get, and fn are all continuous but f is not continuous. We know that if fn converges to f uniformly, then f should be continuous. But if we get the limit function is not continuous, whether fn are all continuous, wherever fn are all continuous, then we can say that this convergence is not uniform. So in this respect we can use this result to show a convergence is non-uniform. For this we have taken here this example. Let fn x equal to tan inverse nx for x belongs to 0 to 1. Then we say that, see that for x greater than x equal to 0, actually tan inverse 0 equal to 0, therefore fn converges to 0. But for x greater than 0, tan inverse nx for n tends to infinity, this converges tan inverse infinity. Tan inverse infinity means pi by 2. Therefore limit n tends to infinity fn x, this becomes pi by 2 for x belongs to open 0 to close 1 and 0 if x equal to 0. Here we see that fn are all continuous but f is not continuous. Therefore we definitely can conclude that this convergence is non-uniform. Actually, in the first class of consequences of uniform convergence, I have discussed these consequences. From these consequences we have 4 results. These 4 results I have discussed for continuity here. Next I am going to next property of consequences of uniform convergence. That is integrability property. Integrability property means if fn, for a sequence of function fn, actually if fn are all Riemann integrable, then whether f is Riemann integrable. F means f is a limit function of fn. Limit functions means that may be pointwise or uniformly, but first I am taking f may not be uniformly continuous. Fn may not be uniformly convergent to f. F is some limit of fn, that is f is only pointwise convergent. Fn is only pointwise convergence to f. Then actually we cannot assure that if fn are all Riemann integrable, then f may not be Riemann integrable. The limit function may not be Riemann integrable. For this we have taken an example. This is a good example actually. Just see it minutely. Take I equal to closed interval 0 to 1 and r1 r2 r3 dotted this an enumeration of the rational points of 0 to 1, that is q intersection 0 to 1, that is all the rational points between 0 to 1. We know that all the rational points between 0 to 1 is countable, therefore we can write these rational points, we can enumerate this rational point as this actually r1 r2 r3 dotted this. And r1 is the first rational number in between 0 to 1, r2 is the second rational number in any respect actually. Now let us consider this sequence of function fn defined by fn x equal to 0 for x equal to r1 r2 dotted rn and 1 for x belongs to 0 1 minus this. Actually at all irrational points fn equal to 1 and it is also 1 at all rational points for excluding r1 r2 rn. That is, if we look into the function, then this is actually given by this f1x equal to 0 for x equal to r1 only. At all other points f1x equal to 1 excluding r1. Similarly f2x equal to 0 for x equal to r1 and r2, and at all other points f2x equal to 1, and so on. Actually f3x, if we take f3x, then it is 0 at x equal to r1 r2 r3, otherwise it is 1. So f1 is discontinuous at r1 only, f2 is discontinuous at r2 only. Since f1, the point of discontinuity of f1 is only 1, that is finite, therefore f1 is Riemann integrable. The point of discontinuity of f2 is r1 and r2, r1 and r2, therefore f2 is Riemann integrable. Similarly fn is discontinuous at r1 r2 rn, fm I have written here fm is discontinuous at r1 r2 rm, that is also a finite number of points, therefore fm is also Riemann integrable. So you can say that f1 f2 f3 dotted fm dotted all are Riemann integrable between 0 to 1. Now we will find the limit of the sequence of functions. Actually the limit will come different for different values in 0 to 1. Different values means if a point is rational in the 0 to 1, then the limit I will get some limits, and for irrational points I will get another limits. So I take rk be a rational points between 0 to 1. Therefore we see that fn rk equal to 0 when n greater equal to k, because we have already defined the function as f1 r1 equal to 0, f2 r1 equal to 0, f2 r3 equal to 0, f2 r2 equal to 0, but f2 r3 equal to 1. Similarly if n greater than k or n greater equal to k, then fn rk equal to 0. Therefore limit fn rk equal to 0 for all, limit fn rk equal to 0, therefore at any rational points rk, limit fn x equal to 0 for x belongs to 0 to 1 intersection q. Similarly, if we consider beta belongs to 0 1 minus q, then f and beta equal to 1, therefore limit n for all n, actually f and beta equal to 1 for all n for an irrational points, therefore limit f n equal to 1. Therefore we get the limit function as fx equal to 0 if x be rational and fx equal to 1 for x be irrational. We already seen that f is not Riemann integrable. So we see that fn, the sequence of functions, we have taken the sequence of functions fn where fn are all Riemann integrable in between 0 to 1, but the limit function f is not Riemann integrable. Also we can prove this convergence is not uniform convergence. That is the previous, we can do this by previous parts actually. Next question arises this: suppose fn is a sequence of function where fn are all Riemann integrable, and the limit function f is also Riemann integrable, but whether limit n tends to infinity integration a to b fn, that is, we find the integration of fn on a to b. Here I have taken I equal to a to b actually, the interval I equal to closed interval a to b. We find integration a to b fn for all n, then we will get, certainly we will get some real numbers and a sequence of real numbers. Then we take limit n tends to infinity of this, then whether it is equal to this, that is, if we alter the symbols limit and integration, then whether the equality occurs. Actually these also may not occur if the sequence of function fn converges pointwise to some function f. In this respect, I have taken another example fnx equal to nx into e to the power minus nx squared for x belongs to 0 to 1. We see that for x equal to 0, fn0 equal to 0. Therefore, limit fn0 equal to 0. For x belongs to 0 to 1, open interval 0 to 1, we see this. Actually, e to the power nx squared, if we expand this, we get this. All terms are positive. We have taken only one term. Therefore, e to the power nx squared is greater than n squared x to the power 4 by 1. If we take the reciprocals, then the inequality sign changes. Therefore, since e to the power nx squared are all positive, nx is also positive because x, we have taken x between open interval 0 to 1. Actually 0 open this. Therefore, we get this. Here limit n tends to infinity 2 by nx cube it equal to 0. Hence, by Sandwich theorem, we get limit n tends to infinity this equal to 0. That is, limit n tends to infinity fnx equal to 0. Therefore, the limit function f is given by fx equal to 0 for all x belongs to 0 to 1. That is, here f is Riemann integrable because it is continuous. Also, the Riemann integration between 0 to 1 of f is 0 actually. Now we find the Riemann integration of fn. Actually here fn are all continuous functions, therefore actually it is a combination of polynomial function and exponential function, because fnx equal to nx into e to the power minus nx squared. So it is certainly continuous, therefore fn are all uniformly continuous. Fn are all continuous functions, therefore fn are all Riemann integrable in between 0 to 1. And the Riemann integration, actually if we find the Riemann integration, then it becomes this. I did not give here the calculation, it is very easy calculation. So limit n tends to infinity integration 0 to 1 fn, it becomes actually e to the power minus n tends to 0 as n tends to infinity. Therefore this limit becomes half. This limit becomes half. But integration 0 to 1 fx equal to 0. Therefore we get limit n tends to infinity 0 to 1 fn. This is not equal to integration 0 to 1 limit n tends to infinity fn. Actually, if this property, if equality occurs, then this property is known as term by term integration. Term by term integration, it is called term by term integration, since first we take the integration of all the terms of this sequence of functions, then we take the limit in the left side, and in the right side we take the limit of fn first and then integration. If equality occurs, then we say that the term by term integration is possible. But here in this example we see that if fn converges to f only pointwise, then the term by term integration may not be possible. In the next theorem, we see that the term by term integration will be possible if the sequence of function converges uniformly to some function f. Here is also the uniformly continuity is a sufficient condition to hold this result. These results mean term by term integration. So I am going to prove of this theorem. Let fn be uniformly convergence to f. Let epsilon greater than 0. Therefore, for there exists some positive integer k. There exists some positive integer k such that these results holds. I have taken in the place of epsilon as these values, epsilon by 4 into b minus a. This holds for all n greater equal to k and for all x belongs to I. Therefore, for n equal to k, this result holds mod of fkx minus fx. This is less than epsilon by 4 into b minus a for all x belongs to I. If we break this, expand this modulus, then we get for all x belongs to I these results. Since fk is Riemann integrable, therefore there exists a partition P of AB such that upfk minus lpfk less than epsilon by 2. Here we take actually the partition as this will be required actually in the next part. For p equal to, here we take p equal to x0 x1 x2 xn. In general we take this partition actually. Now let capital M r equal to supremum of f for x belongs to xr minus 1 to xr. Small m r into equal to this capital M r dash and capital small m r dash. We have taken capital M r dash and small m r dash are supremum and infimum of f of k in this interval actually for r equal to 1 to n. This for r equal to 1 to n. Therefore, in the from this result actually, from this result we see that the infimum of fkx, that is small m r dash minus epsilon by 4 into b minus a, must be lesser equal to infimum of fx. Similarly, supremum of fkx, it will be greater than, actually supremum of fkx means capital M r dash plus epsilon by 4 into b minus a, it will be greater equal to m r, capital M r. So we get these results, small m r dash greater equal to this and capital M r lesser equal to this. If we take here the minus sign, it will become plus and the inequality becomes lesser equal to, then capital M r minus small m r, this becomes lesser equal to capital M r dash minus small m r dash plus epsilon by 2 into b minus a. We take summation from r equal to 1 to n in both sides, then it becomes upf minus lpf. This becomes upfk minus lpfk and this becomes epsilon by 2. Therefore, we already got upfk minus lpfk less than epsilon by 2 for this partition P. Therefore, this is less than epsilon for this partition P. Hence, we can say that f is Riemann integrable on AB. The first part of this theorem is proved. That is, if fn is uniformly convergence to some function f and fn are all Riemann integrable on AB, then the limit function f is also Riemann integrable on AB. Now the next question arises, the equality of the limits, that is limit n tends to infinity integration a to b fn equal to integration a to b limit n tends to infinity fn, whether it equals. Actually this part is not so hard, it is very simple. Actually we already got this definition. Just take this integration a to b mod of fkx minus fx dx mod of fnx minus fx dx, this is lesser equal to integration a to b mod of this fnx minus fx dx. We already get mod of fnx minus fx, this is less than epsilon by 4 into b minus a, so we put this less than epsilon by 4 into b minus a, therefore we get here less than, actually integration a to b dx equal to b minus a, integration a to b dx equal to b minus a, therefore it becomes epsilon by 4 only, that is less than epsilon. Therefore for all n greater equal to k, actually therefore we get limit n tends to infinity integration a to b fn equal to integration a to b f this, therefore the term by term integration is possible. This f actually integration limit n tends to infinity fn, therefore if we alter the limit and integration, the equality occurs, and for this occurrence actually we need the uniformly convergent. Therefore uniformly convergent is also sufficient condition for this result, actually for term by term integration. Here also a question naturally arises, that whether this condition is necessary. We get same result here also, the answer is no. For this we consider the same example, actually fnx equal to nx by 1 plus n square x square for x belongs to 0 to 1. We know that this function is pointwise convergent. This sequence of function pointwise convergence to some function f, where fx equal to 0 for all x belongs to 0 to 1. Therefore integration 0 to 1 fx equal to f equal to 0. But if we take integration 0 to 1 fn equal to this, actually for now we have to find the limit n tends to infinity of this. We know that limit x tends to infinity log of 1 plus x square by 2x equal to 0. You can use L'Hospital L'Hospital's rule to prove this. Hence by sequential criteria we can say that limit n tends to infinity integration 0 to 1 fn, that is actually 1 by 2n log of 1 plus n squared, it becomes 0, that is the equality occurs. Therefore you can say the for the equality condition, for existence of the equality condition, the uniformly convergent is not necessary. So the condition of uniformly convergence is not a necessary condition, but only sufficient condition for this result, actually. Again we can use this condition for non-uniform to prove some convergent is non-uniform. That is, here we consider fnx equal to nx into this 1 minus x square whole to the power n for x belongs to 0 to 1. We see that the limit function f equal to 0 for all x belongs to 0 to 1. But therefore integration 0 to 1 f equal to 0, obviously. And we get integration 0 to 1 fnx dx equal to n by 2 into n plus 1. Therefore limit integration 0 to 1 fnx equal to half. This is certainly not equal to 0 to 1 f. Therefore the result of term by term integration is not satisfied. So actually we got in the theorem that if fn converges uniformly to some function f, then the result is true. Since the result is not true, therefore fn is not uniformly convergent to f, obviously. So we can conclude that this convergence is not uniform. Actually these are the two properties. There is another properties for differentiability, that is also same result, actually term by term differentiable whether exist or not. Actually the integration is replaced by differentiation only, nothing else. This integration is replaced by ddx. you go through the theorem in the book. I am not discussing the theorem. The proof of the theorem is very large. If you have any problem in anywhere in the proof, then you may ask me in the comment. So I am concluding this class here. I request you to subscribe my channel, and if you like the video, just press a like button. Okay, thank you.